Hi, everyone, and welcome to our webinar. I'm Gary Jesch of Power Transmission Engineering, and I'm happy to present this webinar by our good friends over at DieQua Corporation. Power Transmission Engineering is the industry-leading magazine for technology updates, and our program today is called Selecting and Sizing Electromechanical Screw Jacks to Replace Hydraulic Lifting Systems. It'll be presented by Michael Quas, President and co-owner of DieQua Corporation, located in Bloomingdale, Illinois. Good day, Michael, and how are things looking up in Bloomingdale today?
They're very good, Gary. Appreciate you asking. It's finally a sunny day here after a very long winter.
Welcome to spring, right, Michael?
Exactly.
All right, so Michael Quas is the president and co-owner of DieQua Corporation. He's a degreed mechanical engineer from the University of Illinois, and he's the second generation owner of DieQua, has been serving as president since 1998. And Michael's also active on a daily basis on the engineering and sales floor and is constantly working with customers, creating engineered solutions to a constant stream of power transmission applications. So Michael, today we're going to be talking about this widespread push in North America to replace hydraulic lifting systems with electromechanical systems. Now, we note that the trend has been going on for many years in Europe and is now really taking hold in North America. Many engineers are now tasked with the job of eliminating environmentally unfriendly hydraulic oil with systems that are purely electromechanical. And when making the changeover, a number of important factors need to be considered to make sure that the new design will work properly, efficiently, and reliably over the life of the system. So folks in our audience today, this webinar will walk you through the critical engineering factors that need to be considered, and then we'll create a multi-jack lifting system complete with the performance data, the 3D drawings, and the bills of material. So with that being said, Michael, let's go ahead and get you set up here to show everybody your slides, and we'll turn it over to you today.
Sounds good. Thank you very much, Gary. Appreciate the intro. So as Gary had mentioned, today what we're going to be talking about primarily is there we go, is what are the application, what are the steps necessary to kind of design a system, but primarily one of the reasons for this is that, as Gary had mentioned, there's a big push to convert hydraulic systems over to screw jack systems. Primarily, the main reason is to get rid of the hydraulic oil and the source of, or to eliminate the chance of leaks and the mess and the cleanup and so forth. And quite honestly, screw jack systems can be do have a couple of advantages that are over hydraulics. They are generally a little bit simpler to install from an electrical standpoint. They're fairly accurate and repeatable as compared to hydraulic systems. And the speed and positioning of the systems generally can be controlled pretty easily as well.
Michael,
also, depending on the pitch of the screw or the type of jacks that you use, they also could be self-locking. So there's a bit of a safety element here as well, in case you lose power, or from the standpoint of hydraulics, there's a major oil leak, or you blow an oil line. What we want to cover today is we're going to go over the couple of jacks, the two major designs that are available in the market, review the required data that we typically need when we do a selection. Within our downloads, there is a very convenient parameters checklist, and this is a document that helps us make sure we have all the data necessary to do the sizing. And then we actually want to go through the selection process, and when we do that, there's a couple very critical calculations that we need to do to make sure that we are making the right selection. And then after we kind of review those, we're going to do an actual application. This is actually kind of a cool one in the sense that it is a high-end garage, and it's lifting kind of high-end cars from upper story down to a lower story, for instance, for guys that have expensive cars. And then in the end, we'll show the actual drawing and a 3D rendering of what the system looks like. So let's jump into it. So these are the two styles of jacks that you will typically see on the market. The one on the left is called the standing version. This one actually is where the spindle, as you put input into the drive shaft, I'm going to see if I've got my arrow, there it is. If you put rotations into this drive shaft, this spindle will move up and down So this will then move up and down as with the input onto this drive shaft. The other type is called a rotating version, where as you spin this, the spindle rotates and the nut will move up and down the spindle. So those are the two major versions of screw jacks. What's very unique about this particular program is that it is kind of based on a Lego building block system, if you're familiar with that kid's toy. This is a system by which it's extremely modular. So you can see that for the standing version, you have many accessories that you can actually introduce to the system with line shafts, gearboxes, drive motors, encoders. There are brakes that can be put on the system. And if you look down here, we can also incorporate ball screws. Typically, a standard unit would have what's called an Acme screw, which is a mechanical screw, and then ball screws, I'm sure are very familiar to the audience. They use rolling balls that go up and down the spindle guides. This is similar over here on the rotating version. You have, down here you had the accessories associated with the protection tube that as the spindle goes up and down, but here you've got a series of different types of nuts and so forth that can go on the spindle to go up and down depending on what your application calls for. So that's that kind of shows the modularity of the system. The program itself is pretty extensive. We have, if you can see here, there are jacks that go from 1,000-pound capacity all the way up to 100 tons. We also have a jack down here that goes down to about 500 pounds in terms of capacity. The next slide is kind of an interesting one because it really kind of goes into a little bit about some of the internals of this particular product, which are very relevant in terms of longevity and durability of the system itself. This is the actual worm set that's inside the gearbox, and in our case, this is a steel worm that's hardened and ground. The teeth are ground as far as the finish is concerned. And this is the bronze wheel that the spindle moves up and down inside of. We're going to talk about the other major feature a little bit later in the program here that really sets this design apart from many others that you see out in the market space, and that's how this thing is lubricated. There's actually two compartments in here for lubrication, one for the spindle itself and one for the jack. And that's very, very important in terms of making sure that you don't have contaminants that get into the gearing and substantially reduce the life of the gearbox. You'll also notice that we have two different designs. There's one that with these fins, and then there's also one that has very smooth sides. This one was developed for folks that require a wash down or a cleaner environment where they don't want things settling into the fins, if you will. So the types of information that we need when we do an actual sizing of the gearbox is clearly what's the weight, what's the load, how much are we lifting, the distance that we want to move it, and not only do I need the distance of the that we want to move the load, but I'll need the overall distance of the spindle, that is the room above it and below it that you may need for mounting purposes. So you need the total length as well as the effective lifting stroke. The lifting speed is of course important because that helps us figure out how fast we need to do the input and or what type of spindle to use. And duty factor is also very important. Duty factor is the amount of time, or is the percent of time in a given hour, let's say, that the device is actually being used. Screw jacks, generally speaking, function best in applications that are somewhere in the range of 10 or 15% duty cycle or less, and that's usually because of heat dissipation. But if we're using ball screws, there is an opportunity to go to higher duty cycles. And then, of course, what type of jack to use. That was the R or the S that we had mentioned earlier. The type of input power is also important. And what we mean here is you can drive this with a motor. You can drive it with a servo motor. You can drive it with a gear motor, for example. And also whether or not we need a brake mechanism or not, depending on how fail-safe you want to make the system, so that in the event that you lose power, you don't want the thing coming crashing down, obviously. So there are certain calculations that we need to make to determine whether we require a brake. Operating conditions is important. That helps us determine, how we have to cover the spindle and protect the spindle, or what type of lubricant that we need to use. In other words, if we're in a super hot condition or a super cold condition or a very dirty environment, like a machine shop where you've got a lot of, metal shavings and so forth flying around, for example, things of that nature. So we need to kind of get an understanding where these things are going to be put. And then the final piece of information is the operational layout. And by that we mean, is this a single jack? Is it a multi-jack lifting system? And if it's multi-jack, what's the configuration? And we'll look at that in a little bit more detail. Okay, so we have, as part of our website, there's a download for a application guide, and this is one page of it. This is also in the main catalog, but this is the application checklist that I was referring to earlier. And in the checklist, we just kind of ask a whole lot of questions, and if the customer can fill this out to the best of their ability, that really helps us out a ton in kind of prepping and doing the initial calculations, and then fine-tuning it as we come into more conversation with the customer. A couple additional pages in the application guide are these 2 pages, and this is again part of that Lego building system that I mentioned earlier. Here you can kind of check off, depending on which style of jack you're looking at, whether you need a brake, whether you need a certain type of nut, whether what type of rod end makes the most sense. Oops, sorry. What type of rod end makes the most sense for your device, and so on. And this is also part of the checklist, and this is when we're talking about the layout. So if it's a 4-post jack or a 3-post jack, where the drive motor is in the mechanism and so forth. This page is important to us because it helps us calculate what the overall input power is based on all the components that motor or gear motor needs to drive. And we'll run through that as an example a little bit later. This is kind of an important page. This is actually the thought process we go through, and we're going to follow this as we do the calculations in this selection process. And this is basically a flow chart for the decision making that one has to go through when sizing the gearbox. So the first thing one has to figure out is whether you're going to do a rotating version or a standing version, and then the corresponding calculations based on that selection. So you don't have to spend a lot of time on this sheet, just know that there is a flow chart and thought process, and we're going to follow that, and you'll see how that works out. So I had alluded to earlier that there are some very critical calculations that are necessary in addition to just figuring out what the capacity is and which jack to use. But in that selection process, there's a couple of things that are kind of important to calculate. One of them, and the one on the left side here, is what's known as the buckling force. And the buckling force, it's shown a little bit graphically up here. In other words, that is the capacity of the spindle to remain rigid. At some point, based on its diameter, if you exceed a certain force, it's no longer able to sustain that force and it will buckle. And based on the loads that the customer is looking to push, we need to calculate the diameter of that spindle, the minimum diameter of that spindle, so that it does not buckle. And that's one of the critical calculations. The other is on the very next page, and that's called the whirling speed. In other words, as the spindle rotates, we need to figure out what's the critical speed at which it'll start to wobble. And there's a calculation mechanism in there as well. So once we determine how fast we need to drive the system based on the lifting speed the customer is looking for, we compare that to what the maximums are, and we then are able to say, okay, the jack that we selected is of the proper size and won't exceed that maximum critical speed. So the next thing, of course, is in the process is determine the amount of torque necessary to drive the overall system, and that is located on these 2 pages. Now, again, we don't have to; these are hard to see in this in this presentation when they're so small like this. But as we go into it, these pages will blow up, and we'll run through the calculations pretty succinctly. So Lubrication is also a very, very critical part of a screw jack. And this shows something that's very keen about the system here. This is the rotating version, and it's showing the Acme style over here and the ball screw style on this side. So this yellow is indicating that there is a cavity inside the screw jack for grease. You can see that these are complete axial bearings because the load is obviously in an axial fashion. And what you see here kind of in a green on the screw itself is the lubricant that gets injected directly from this nut here onto the spindle. In the ball screw application, there is an injection port on that nut as well. So these two boxes on the bottom are the same, so the internals are the same. And a similar mechanism exists for the standing version. But what I really want to point out here is that the standing version is really the only one, this one, the Zim product that we produce and offer here, is the only one where this green cavity is completely separate from the yellow cavity inside the gearbox. Most of the manufacturers that you see domestically, as well as from other parts of the world, this is one cavity. In other words, all the debris that might accumulate on a greased spindle will eventually get inside the mechanism here, and that has an impact on the life of the gearbox. On the Zim product, they are completely separate cavities and can never mix. So let's do a typical lifting application. As I mentioned to you earlier, this is for a 4-post lift that a customer came to us not that long ago. It's about 6-8 weeks ago, I believe. They came to us. This is a company that makes high-end auto lifts. Most of their product up until recently has been hydraulic, and they've had a lot of their customers asking for electromechanical solutions, screw jacks in other words. So they came to us with a series of drawings. This is with the lift in its upper location, its upper position, if you will. This is in the lowered position, and the third one is the one that gives us a lot of information. This is the isometric view. So this is showing the basically the guide mechanism, and that's another point of information that I didn't touch on earlier, which is extremely relevant to speak of, in that these electromechanical screw jack systems work best if the load is guided. In other words, there is some kind of mechanical element in the corners or along the axis of movement that guides the system, and it does not rely on the jack itself to guide it. That allows us to actually make the system a little bit smaller in terms of spindle diameters and so forth. Otherwise, if the jack is required to do the guiding, it has to be upsized. So in this case, it's a guided system, which is quite helpful. So the customer came to us, and they submitted to us an application checklist. So they had a lot of data in here. What they're telling us is that the overall load, as you can see here, is around 10,700 pounds. And that's actually the car plus the platform itself. They're saying it's in a vertical application. It's a smooth lifting. In other words, there's a motor that we assume that is driving this thing, and it's going very smoothly up and down. They're telling us that the lift height that they want to go is 96 inches or 8 feet. They're telling us also that the speed that they want to achieve is about 8 feet in 19 seconds. So they want to lift and lower from the basement up to the driveway in 19 seconds. What is also important for us is we kind of try to get some information so we can figure out duty cycle. And in this case, he's telling us that they're going to do this a maximum of 8 times a day, up and down, roughly. It could be a little bit more, could be a little bit less. So when we do the math, that comes out to about 5 minutes of total runtime in any 24-hour period, or a duty cycle of less than 1/3%, or right around 1/3 of 1%, which is way, way under the 10% or 15% limit that we try to maintain for the jack. So we don't have an issue with duty cycle. They're telling us that they want a rotating version, and they're telling us that they want to drive this thing with a 3-phase motor, but they're not sure whether or not they need a brake or not. That's something that we'll have to help them with. Dry conditions, ambient temperatures around 40 to 90 degrees Fahrenheit. So, and then they were kind enough to send us the drawings, which we just took a look at. So this is a tremendous amount of data. Is very useful for us to help us figure this thing out. So how do we spec a screw jack system for this kind of application? Well, we go back to this procedural drawing, this flow chart, if you will. We know it's a guided system. We've got the parameters that were sent to us via the checklist. Customers told us that it's an R version, so we're actually going to go down the right side of this page in terms of the thought process of figuring out which jack he needs. So the initial jack selection, let's take a look at that. The customer did tell us that the total load is the car plus the platform. So I just did some kind of calculations here, and you guys can follow along fairly straightforwardly. So the car that they're telling us that is going to be a 7,000 pound limit for the elevator. The hardware, the platform itself, and everything else that's moving up and down is another 3,700 pounds. So we're at roughly 10,700 pounds, and when you convert that to kilonewtons, it's around 47 kilonewtons in total, and that puts us into a 50 kilonewton jack. That's the next larger size jack that can accommodate that particular amount of lift. Excuse me. Some important data that we're going to need to know is the gear ratio of the gearbox, and that is on this page for the 50 kilonewton jack. It's actually right here. And we need to know the screw pitch. In other words, the pitch of the screw is how much vertical lift do I get in the screw per revolution of that screw. And we know from this data, this is a trapezoidal screw, and it's a 40 millimeter diameter screw, and the pitch is 7. So we know that from this data that we have a 7 millimeter pitch. Now this data actually comes from a catalog page, and as you go to our website, which we'll show you the links at the end here, you can download this catalog very easily, and this is page 23 of that particular catalog. And every single jack that I showed you in that product overview has its own page with this data on it. The checklist is in there, and all of the sizing calculation work that we're going through is detailed in there as well. So the next thing we need to do is figure out the spindle that we want to use. I have 2 pages out of the catalog here. This is the one that we just looked at. This is the 50 kilonewton jack. This is again towards the beginning of the catalog, and this is using an Acme screw. I showed you in that exploded view earlier that we also have the ability to use ball screws. So the 4 different spindles, actually, or 5 different spindles that we can use on this gearbox is an Acme screw. And over here in this section, it's a little hard to see here. We're going to see blow-ups of this page in just a moment. There are 4 different pitches available for ball screws. So let's go through the calculations and how to figure out which spindle that we actually need. The calculations that are relevant here is to figure out the lift rate, right? So the spindle selection that we're going to go through based on the lift rate. So the customer told us that they wanted to lift this thing at 8 feet and 19 seconds. And when we do the calculation, that comes out to about 129 or 128.4 millimeters per second. So if we now calculate the gearbox drive speed with that data, and that is basically the lifting speed, which we just calculated in millimeters per second, times the gear ratio of the gearbox divided by the pitch of the screw. That's why we needed that particular data. So in this case, it's 128.4. In essence, times 1, these cancel each other out, but this is revs per second. To get it to RPM, we're at 7,700 RPM if we were to use that spindle, that Acme spindle, and that is way too fast. Again, if you look here, the maximum drive speed of a gearbox is only 1,800 RPM, so we can't use that spindle because we just simply cannot drive the jack that fast. So now what? So now we have to take a look at the ball screws, and we need to kind of figure out which pitch makes sense for the speed that that customer is looking for. And that's kind of what I went through in these calculations. So if we solve for pitch, utilizing the maximum lifting speed, which was 1,800 RPM, and we solve for that, we get the pitch is equal to the lifting speed times 60, which puts us into RPM, times the gear ratio by the maximum drive speed allowed for that jack. So that's 128 times 60 7 over 1800, and that means I need a pitch at minimum of roughly 30 millimeters per revolution, and quite honestly, that puts us into a 40 pitch screw, which is this guy right here. So it's a 40 by 40. It's 40 millimeter diameter, and the pitch is 40 millimeters. So it'll rise 40 millimeters with every single rotation. And when I calculate what the input speed is now plugging in a 40 pitch, I come up with a speed of 1,344 RPM on the input of the gearbox to give me that lifting speed using that spindle. Now I realize I'm jumping through this stuff very, very rapidly, and again, this is something that we do every day. You're welcome to go through these calculations as well. It's not that complicated. You just have to run through a few of them, and then it comes pretty quick. So again, I was using the data from these two pages. This is the page that has the data for the Acme, and this is the page that has the data for the ball screws. So now going back to that flow chart, we got to figure out what the buckling forces are. There are 3 formulas that we use here, and we're going to use this third one because it applies to the type of jack we are using, which is the rotating version. And we are also know that it is a guided system. There's a calculation for a standing version that's guided, and there's a calculation for a standing version that's unguided. So blowing up that page, don't let these big calculations scare you. Most of these numbers are constants. They just kind of plug into a calculator and you come away with it. And of course, the bottom data here, which is on that page, is relevant to us. So let's run through this real quick. So the buckling force is basically the total, the force associated per jack is basically the total force that the customer informed us of, which was this 10,700 pounds. And we're going to divide that by 4 jacks because the customer told us it's a 4-post system. So that means that each jack has 11,900 newtons of force being exerted upon it. And as we go through the calculations, which is all here, we come up with a core diameter of that spindle. In order to be able to lift that spindle needs to be at least 34 millimeters in diameter. And if we go down here, you can see the ball screws, and the various sizes of jacks and what the core diameters are. So this puts us into a Z35 or a Z50 jack. And in our case, it's a ball screw with a diameter of 40 millimeters that has a minimum core of 34.1. So we know that we're into a size 50 jack. So each of the 4 spindles will be a size 50 jack. Then the whirling speed is important. And again, we're going to use this page from the catalog. And as we go through the calculations here again, we know that the spindle from our design will be captured at the top. So this factor, which is part of the formula, here's the formula. It's 0.8 times the theoretical critical speed times a factor. In this case, the factor is 1. So as we go through this calculation, we need to determine, first of all, what our actual speed is, as well as what the theoretical maximum speed is. So if we calculate what speed we're doing, the input drive speed, which was 1344, divided by the gearbox ratio of 7, so we know that the spindle is rotating at 192 RPM. This is the maximum speed that is allowed for that particular spindle, and that's using this formula over here, again, the 0.8 times the 350 times 1. Now, where'd the 350 come from? The 350 came from the length of the overall spindle, which we know from the design is close to 3,000 millimeters long, because they told us what the overall height is that they wanted to push this thing. And we know that we're using this particular size spindle, which is a 40 millimeter spindle. And as you come down this chart and we come up here, we come across, and we're estimating that this number should be 350. We do the calculations. The maximum whirling speed is 280 RPM. Our speed is less than 200 RPM, so we know that the speed is okay. So next thing that we have to calculate is the drive torque. And we're going to use this page of data, and as I blow this up, you can kind of see what we're going to be doing here. So here's the drive torque calculation, where we're taking into consideration the efficiency of the gearbox. We take into consideration the efficiency of the screw, and a number of other factors that are in the charts here below that are easily found. So again, let's run through our own example here. So we got 11 per jack, if you will, again, was 11,900 newtons or 11.9 kilonewtons. We know the pitch is 40. This is the drive torque that we're trying to calculate. The idling torque, which is it's the torque necessary to get the jack moving, if you will. And then we plug all of these things into this formula. And we determine that at the end, we need 14.58 Newton meters to drive a single jack. That's the calculation that we're doing here. Now we have to drive a system. And a system calculation means that we need to look at some additional pieces of information in the catalog, namely this one down here. So let's blow that up. And we know we have a 4-jack system, 1, 2, 3, 4. And in order to have a 4-jack system, we have to introduce a couple of gearboxes and some line shafts. And when you do that, all of these elements require a certain amount of torque also to get them to move, in addition to the torque necessary by each of the jacks that we just calculated. So if we know what the layout is, we can pretty quickly determine what the overall torque is. So here's the overall torque number. It's the single jack torque that we just calculated times 4.9. And then we also add a safety factor in this case of 1.4. So as we come back over here, you can kind of see what it is. So it's a single jack drive, which we just calculated before, 14.58 times the 4.9 times the safety factor, gives us to an overall driving torque of 100 Newton meters. Now that being said, you got to get this thing into motion, which means you have to overcome static friction. And there's a certain amount of torque necessary to overcome static friction. And the folks here at Zim have calculated, generally speaking, that's about 50% more than the drive torque. So we multiplied the overall drive torque by 1.5, and that gives us 150 Newton meters is what we absolutely must have to overcome drive torque and drive this system up and down. And then from that, we can easily calculate the size of the motor that we need, which is a fairly straightforward calculations for most of the mechanical engineers that are involved in this kind of stuff. So it's torque times the drive speed divided by a constant 9550 brings us to a motor size of 21.14 kilowatts, or a 28 horsepower motor minimum to drive this system, which would put you probably into probably a 30 horsepower motor. Now this is a judgment call a little bit. You know, you could probably go to a 25 horse motor simply because you're spiking the motor to be able to overcome the static friction here. So generally speaking, we probably could get away with like a 25 horsepower motor for this particular system. So all of that being said, and going through all of those calculations, we can very quickly come up with a drawing for what the customer is looking for. And in that case, instead of having the motor come from this configuration, he wanted it over to the side. He did want to add a brake because we recommended that he add a brake. As a matter of fact, we recommended he put in 3 brakes. There's a brake here, here, and then there's one on the motor. Because it's a ball screw, it's not self-locking, especially with the pitch that we had called out or selected here. So if we do lose power, we want the brakes to engage, or if the system comes to a stop, we want the brakes to engage. So we don't drop a very expensive car 9 feet to come crashing down to the floor. That would be bad. So this is what our drawing looks like. It has a full bill of material associated with it. It has the full spindle length associated with it, and has a lot of the detail as far as the components. I also want to point out, as I kind of call up the next drawing here, this is kind of a scaled isometric view, 3D view of this thing. And you see a lot of line shafts in here. This is a fairly long distance. I can't remember what it was exactly, but it's something like 12 feet. and we cannot put a line shaft extending that full 12 feet. So there were some additional calculations that we needed to do to figure out the line shaft size and length, but I didn't really want to go through all of that detail here. It's fairly straightforward. It's in the catalog, and here you can see the jacks, the 50-ton jacks, or the 50 kilonewton jack, excuse me, and you see the ball screws, nuts here, and then this is the ball screw spindle. At the top of the spindle, we have a fixed plate so that it's in essence guided. This is not in free space up here. We have two spiral bevel gearboxes. This is a T configuration. This is an L configuration, and then we have in essence a foot-mounted motor. In this case, probably a 25 or a 30 horsepower motor. So that's in essence how we go through figuring out how to size a screw jack. So as a quick recap, basically you need to take a look at the overall load. You need to understand the lifting speed so that we can calculate what kind of spindle that needs to be used. We calculate the buckling forces and the whirling speeds to make sure that we're sizing the jack with the right spindle diameter. And then we calculate what it takes to actually drive the entire system based on a number of factors that we went through. And then the rest of it is just layout and selection of components. So all of this is available on the page that I'm showing you here is our website, which is DieQua.com. Excuse me. As you read through the website or glance through the website, you'll go to the products page, and towards the bottom of the products page is actually where you will find all the screw jacks. You'll find many other products on the DieQua website as well, because we're primarily a power transmission, mechanical power transmission house, where we design and build many different types of gearboxes, and the screw jacks is one element of what we do. But when you get to the screw jack part, there's links to YouTube videos there, and there's really an interesting new tool, which is an online configurator, and I would invite anybody to kind of play with that a little bit. It does most of these calculations behind the scenes. You just have to go on the system, you have to register, and then it gives you full access to a product selection through that configurator, and as I said, it'll do many of the calculations behind the scenes, so it's pretty foolproof. And in the end, it will give you a 3D drawing and all of the parameters that are appropriate for that particular system. Clearly, there's also PDF catalogs you can download. The application guide is in there to download. So it's a great system. It's a building block system, and I would invite all of you to kind of check it out. So Gary, that kind of I think brings us to the question and answer portion of the program here, and I'll hand it off back to you.
Great, thank you. Great job of presenting that material, Michael. Folks in the audience, our attendees, we invite you to send in questions through the GoToWebinar interface here, the control panel. You can just type in your question under the questions tab there. If you'd like to have Michael take a shot at answering that. And we also have on the call here with us Roberto Vasquez, who's one of the engineers there at DieQua. Hello, Roberto. That pretty well covered things here today for us, didn't it?
I think so, yes. But let's leave it to the group and see if there's specific questions that we could address now, or we could also invite them to reach out to us later on.
Excellent. And tell us a little bit about your qualifications there, Roberto, would you please?
Sure thing. I've been with DieQua in May. This coming May will be 11 years. I'm a mechanical engineer graduate out of the University of Illinois.
That's why I hired him, by the way.
Coincidence? Yes. I started off as inside sales support, and I've then progressed to application engineer, and currently I'm the supervisor for the inside sales group.
Excellent. So I do have a question here for you, gentlemen. One of our attendees asks, can I use this for continuous operation? You
want to chime in, or?
Yeah, I'd be happy to answer that. The idea with these screw jacks are for fine position adjustment. As Michael mentioned earlier, these would be best suited for 10 to 15% duty cycle, mainly to help alleviate heat generated on the screw jack. Of course, if more frequent operations is necessary, we could look at re-rating the jack body and also going to a ball screw mechanism.
Okay, excellent. And some of our viewers are asking about getting access to your presentation, Michael, afterwards. And I would like to say that we are making a video recording of this presentation, and we'll be presenting it off of the Power Transmission Engineering website. We'll be sending that link out with our follow-up email about 24 hours from today. So that'll come out tomorrow morning to you folks. And then you had said something also about the possibility of having documentation to accompany that, Michael.
Correct. Yeah, we'll put some kind of PDF together of at least some of the pages that we the important pages as far as buckling force and sizing calculations, things of that nature. We'll get that into some type of handout. We'll make that available as well.
Excellent. Thank you very much. Roberto, I think there might be another couple of questions here. Do you want to help bring up the next one? That would be your turn.
Sure thing. Does DieQua manufacture the screw shafts?
The screw shafts. I'm assuming if you're asking if you manufacture the spindles, so there's a couple, I'm going to interpret your question maybe a couple of quick different ways. We work together with a company in Austria that's actually the main manufacturer of this system, which is called ZIM. What DieQua is basically ZIM North America. So we work in complete partnership with ZIM. ZIM currently produces all of the spindles, with the exception of the ball screws themselves. So all of the Acme screws they actually make themselves. And what we do here in Chicago, we're in Bloomingdale, a suburb of Chicago, we are a full assembly center for the ZIM system. In other words, with the exception of the much larger sizes, we have the ability here to, fabricate all of the various components to length. The line shafts, the spindles have to be cut to length. Every system is unique in terms of length and so on. And we do all of that fabrication and assembly here, where the actual components are mostly produced by our supply partner out of Austria. Hinge mounting, yeah. We have another question here. Does DieQua offer hinging mountings of the gearbox body? The answer is yes. There is, I don't have the presentation open at the moment, but when I showed you the overall view of the gearbox, you saw, in essence, and I'm asking people to go by memory, but you can certainly download the catalog, it'll become very obvious. There are some trunnions, if you will, built into the housing of the jack body itself. And then there's some hardware as part of that Lego building block system by which they just slide into those trunnions. Those become the pivot points. And then the units can be used to, for instance, open and close doors, because when you're opening and closing a door, that's on an arc. And then the gearbox has to be able to pivot, and we absolutely have those solutions. Here's another question. In a multi-jack system like the one shown, is there any risk of the jacks becoming out of sync and load becoming off balance? If so, how is that mitigated? They are mechanically linked, generally speaking, but if a line shaft were to fail or a coupling were to fail, then yeah, you're absolutely correct that will become off balance. There's a couple of ways that you can mitigate that. One of the ways is to put a type of sensor, and in our case, they're very simple. The sensors that are on the words are eluding me right now.
Limit switches?
Yeah, excuse me. Yeah, limit switches. I'm drawing a mental blank here. You can put limit switches on the system so that, for instance, in the four corners on any of the individual jacks. So if one becomes out of sync and you trigger one of those limit switches, then you stop the system. So there's a number of ways that you can mitigate that. But clearly, I mean, if something fails, it fails, and obviously when that happens, you want to shut the systems down and repair those components. What kind of linear guides would you recommend for this type of vertical lift? If you're referring to this specific one, this car jack lift, there are a type of, there's a couple of products out there that, in essence, a U-channel that has a roller guide on the inside of it. That U-channel would go up the corners, and that roller guide would become part of the platform, and that would, in essence, be the guide. In this case, there's a whole bunch of different ways it could be done. There's many different manufacturers of linear guides that can be incorporated here as well. So it really is just up to the customer what they'd like to use. Go ahead.
Okay, perfect. Then another question I'd like to read here is for the whirling speed. I think we had shown or displayed the page for whirling speed on a trapezoidal type spindle. Of course, we were then pursuing an application for a ball screw. The concept here is in that the longer and faster the operation, the larger the diameter of the spindle, the core diameter. So while the chart indicates the trapezoidal spindles, the idea can be borrowed also for ball screws, as long as you maintain the same core diameter.
Right, that's why we made that selection of the TR40x7. The pitch wasn't as relevant as the diameter of the spindle itself, or the core diameter of the spindle. In this case, it's the 40 millimeter, which had a core diameter of 34 millimeters.
Okay, great, guys. And I have another one here for you. Are these off-the-shelf units, or what's the typical turnaround time for a system like this?
The components are, generally speaking, off the shelf. What's not off the shelf is the fabricating of the components to make the system. As I said, we have all the screw jack bodies, for instance, are off the shelf. We have inventory of the various spindles. We maintain inventory of fairly long lengths. They're about 6 meters long in our inventory, and then we cut them. We cut them to length and machine the ends to the configurations required for the type of jack that's being used and what the jack is being used for. So we are trying to do relatively simple systems in a time frame of about, my goal here as the owner of this business to get us under 2 weeks, but generally right now we're in the 2 to 4 week time frame with our current workload.
Okay, well, I think that's just going to about cover our topic here today, Michael and Roberto. Thank you very much. If you have one more quick question in the audience there, feel free to send it over. One of our attendees just asked, who do we contact at DieQua? And you can get a hold of the folks here at DieQua by phone or by email. And your questions will be directed to the appropriate person. Roberto, are they probably going to end up speaking with you to get more answers there?
Yes, I'd definitely be one of the main people that they would speak with. So I'll welcome the opportunities.
You know, Gary, I can very briefly, at least over the airwaves here. My email address is just my first initial M and then last name Quaas, Quaas, at DieQua.com. Folks are welcome to send me an email directly if they'd like to, and if I can't answer it, I'll send it up the ladder here to Roberto so that he can apply. Roberto has a lot more, quite frankly. I had him in the room here today because he has just so much more engineering experience on a day-to-day basis with these things. I do get involved daily with them, but not to the extent that Roberto does. So I didn't want to make a misstep, and that's why I asked Roberto to be in the office here, or in the room with me. But if you go to info@DieQua.com, it'll definitely get routed to either Roberto or myself.
Great. Well, it's nice to know that the president and the CEO is ready to roll his sleeves up and jump in to help people out. So that's excellent. I do have one other question coming in here. And the visitor asks, to facilitate a continuous use rather, is there a cooling type available, or is there cooling necessary in continuous use?
Yeah, a lot depends. I mean, in order to keep the heat to a minimum, we'd probably want to go away from an Acme screw. And these are just generalizations here. Everything is very much dependent on the application itself. continuous use for jacks of this nature is tricky. The answer is yes, but it does require a considerable amount of, not a considerable amount. There are special designs that can be incorporated. In other words, we could move away from a worm drive and go to a spiral bevel drive, for instance. There's a number of different things that we can do to eliminate to bring the heat down so that we can get the duty cycle way up. So the simple answer is yes, but obviously we need to do the engineering for it.
What kind of applications are we talking about for continuous operation?
Well, as a matter of fact, I just had a very interesting conversation with Gunter Zimmerman. Gunter is he's the owner of Zim, and he and I work on a lot of different things together. And they just attended a show in the construction industry I think it was in Berlin last week, and they had a number of people approach them from companies like Caterpillar and John Deere. So you can imagine the type of construction equipment out there that has hydraulics on it to move a bucket or to move those types of things. And one would think that's fairly continuous operation, and the reality is it's not. Even though the machine is moving all the time, the amount that the bucket is moving is not 100%. So it could be as high as 20% and 30%. And in those situations, Zim is in the process of coming up with a new program that they're going to bring out later in the year, actuators that can accommodate some of those larger forces with much higher duty cycles.
Well, this has all been great information, ladies and gentlemen. That brings us to the conclusion. And as we said, keep an eye out in your inbox for the follow-up email where you'll be directed to the Power Transmission Engineering website for the recording of this and other information that we're going to be including as a follow-up for the webinar. Gentlemen, it's been a real pleasure to work with you today and to have such a great presentation under our belt now. So thanks very much. And folks out there, have a great weekend. And thank you very much for joining us here at Power Transmission Engineering. Have a great day, everybody.